When evaluating blockchain infrastructure under extreme load, engineers typically rely on raw performance logs to measure system limits. This JSON log is the output from a recent high-volume stress test. The top-line summary shows a flawless execution, 400 total transactions processed with a 100% confirmation rate. Below that, the log records a network ingestion speed of 136.22 transactions per second. Taken together, these three aggregate metrics suggest a healthy, stable system that smoothly digested heavy traffic without dropping a single packet. Transactions per second, or TPS, operates as the industry standard benchmark for network capacity. It is the number most often cited to prove a network can handle commercial scale. But TPS only measures the front door. It tracks how fast a network accepts data, regardless of how long it takes to actually finalize it. When we look past the summary and examine the individual transaction hashes recorded in the underlying array, the data tells a different story. We have to isolate two specific temporal data points for every recorded action, the submit time and the confirm time. These metrics define the speed of ingestion, the front-end acceptance of data, as separate from the final execution of the state change. To understand the origin of that distinction, we first need to look at the config and lane stats blocks of the JSON log. The baseline configuration shows 20 independent senders pushing data concurrently. Each sender routes its traffic through 4 parallel lanes. This prevents sequence failures. Blockchains enforce nonce ordering, a requirement that transactions from a single sender must be processed in exact sequential order. By utilizing this architecture, 5 specific transactions are queued sequentially within each of the 4 parallel lanes. This gives us our total structural payload, 20 senders multiplied by 4 lanes, multiplied by 5 transactions, resulting in the 400 total transactions under review. The resulting lane stats confirm that exactly 100 transactions were sent and successfully confirmed per lane across the entire system. This complex routing resulted in 0 errors and 0 sequence collisions. This parallel lane architecture solves the ingestion problem by organizing the incoming flood of data, but it shifts the physical bottleneck directly to the block creation phase. Let's track that bottleneck by diving into the results array for all 400 transactions. This chart will map our temporal data. The x-axis represents the transaction index, from 1 to 400. The y-axis measures time in seconds. We will isolate the very first transaction from the first sender, starting with SYN1-7-C. The log shows a submit time of just 0.015 seconds, and its confirmed time comes in at 0.028 seconds. That gives us a delta between submission and confirmation of roughly 13 milliseconds. In physical terms, a 13 millisecond delta means the network is digesting these state transitions virtually instantly upon receipt. Observing the progression of the first dozen transactions, we see identical behavior. There is a tight linear relationship between submission and execution. At the onset of a stress test, before any network saturation occurs, parallel ingestion and sequential execution operate in near-perfect alignment. Now, we accelerate the plot to map the remaining sender data, tracing the system's behavior as load heavily accumulates. Tracking the blue line of submission times, they remain linear. This proves the RPC ingestion nodes remained fast throughout the test. But tracking the confirmation times paints a different picture. The green curve bows sharply upward, diverging entirely from the baseline. We can isolate a mid-test transaction from sender SYN1-TAT. The submit time is 0.55 seconds, but the confirm time is delayed until 1.44 seconds. The execution delta has already expanded from mere milliseconds to nearly a full second. Fast-forwarding to the final transactions in the log allows us to locate the peak execution delays. By the end of the test, transactions are waiting over 6.09 seconds for finality. We define this specific visual divergence as the latency drift phenomenon. The cause of the drift is structural. RPC gateways ingest data concurrently, but the blockchain consensus engine is forced to process blocks sequentially. A constant high TPS rate results in compounding confirmation degradation under sustained load. This fully populated chart of the entire stress test visualizes the shape of network congestion. Notice the expanding physical gap between the submission curve at the bottom and the delayed confirmation curve arcing above it. That shaded area represents the visual footprint of the blockchain mempool. It is a measurement of the volume of transactions suspended in memory, waiting in a queue for available block space. It contrasts the parallel capacity of the network's outer edge against the rigid limitations of the core consensus layer. Revisit the 136 TPS metric and the 100% confirmation rate we saw at the very beginning of the test log. The parallel architecture prevented data loss, but the top-line summary entirely obscured the drop in user experience. High submission TPS indicates network capability at the gates, but it determines nothing about time to finality. Actual system performance is defined by the latency delta between the RPC layer and the consensus layer.